Alright, so, guys, listen up. Guys, so, all we've really done up to this point is be able to learn how to figure out two different things. The first thing is, for a chemical reaction, a chemical process, is it endothermic or is it exothermic? The next thing is how much energy is either released or absorbed, okay? So everything we've done up until this point determines if energy is absorbed or released, then how much energy is absorbed or released. So one other thing that kind of fits under the umbrella of thermodynamics in this chapter is we need to figure out if some of these reactions actually happen or not. Okay? So if we predict the delta H for a reaction to be negative 15 kilojoules per mole, okay, it's going to release 15 kilojoules of energy per mole. If the reaction doesn't happen, is it going to release that much energy? No, it's going to release none, right? So it's important for us to know if these reactions are actually going to happen or not. So if we think back when we first encountered that idea of will it happen or not, we were looking at single replacement reactions, correct? So what did we look at to determine if a single replacement reaction would happen or not? The activity series. So if we have potassium plus sodium chloride, we said, is potassium reactive enough to replace the sodium and sodium chloride? And we could say yes or no, then be done. Then for our double replacement reactions, we looked at the solubility table. Okay? But those two types of reactions are a very, very small percentage of the overall amount of chemical reactions that exist and we know about. So we focused on those most of the year because those are simple and they're easy for us to predict the products of. But those two types occur between two ionic compounds. So how do I recognize an ionic compound? What does it start with? A plus ion. A metal. So it starts with cation. So whether it be a metal or a polyatomic cation like ammonium. So there's a lot of chemical reactions out there that don't happen between ionic compounds, especially organic type reactions. And those reactions are a lot more complicated. Okay? We don't have simple activity series that allow us to determine if we can, or if the reaction will happen or not. So the main goal of this today is just to learn a way to numerically do a calculation, then use that calculation to decide if a reaction will happen or not. Turn your notes to where it says part 2. So it gives you a kind of broad definition of thermodynamics. So we're really just looking at all the factors that affect the energy of the system we have going on here. Okay. So we've looked at enthalpy already. Now we want to talk about a new word, entropy. So for enthalpy, we care about the amount, right? The number is important. We've calculated the number. But a lot of times we want to worry about the sign for enthalpy. Is it endothermic or exothermic? Okay. And for enthalpy, have we ever calculated just the value for H? Now we've always calculated delta H, right? The change in enthalpy. So entropy will be the same way. We will typically focus on the change in entropy. Let's say change in. So as you've learned, the symbols can never be easy for this. So, but if it's change in entropy, we know the symbol is going to start with what? Delta, the triangle. So you may know what the symbol for entropy is. A Q.
For real?
No. It's a capital S. Okay. So delta S is change in entropy. So we can fill that in down here. Entropy, capital S. Entropy, we can fill in also H. We know enthalpy is a measure of the change in energy of the system. So entropy, in kind of simple terms, is a measure of randomness or disorder. So it's typed out as randomness. We'll use the phrase disorder to describe it. It's kind of a weird thing to think about, but let's think of a simple example that should make a little more sense. So if you think about ice versus water vapor, are ice and water vapor the same molecules. Yeah, they're both just water, 2 hydrogens, 1 oxygen. But let's talk about what the molecules are doing, what they look like in ice. What do the molecules do, or what do they look like in a block of ice?
They're tight.
Yeah, they're packed in place, right? They're fixed in a nice crystal pattern. They're stuck. Are they completely still, though?
No.
What are they doing? Yeah, they're vibrating around. They're not completely still, but they're locked in place in a crystal. They're just vibrating, okay? So that's pretty ordered, right? It's not very random. It's in a nice ordered pattern. Then if you melt it and vaporize it, you have gas water. So are the molecules the same in the gas water versus the solid water? Yeah. But what are the molecules doing in the gas version of water?
Like moving.
Yeah, they're flying around, right? They aren't just vibrating, they're flying around. There's nothing stopping where they're going. So if you think about using the word disorder, which would you describe as having more disorder? The gas version or the ice version? The gas, okay? So we'll think about kind of more complex examples, but that is initially kind of what we mean by disorder, okay? So you can think about that example. And we care about that because there's a law in thermodynamics, if you take physics, you'll talk about, that overall in the universe, the entropy always increases, okay? Disorder always increases. But for our individual systems we have, the disorder can decrease. We can make it more ordered, but there has to be an equal change somewhere else to counteract that, okay? So I'll try to use the word disorder, and I'll say it becomes more disordered or less disordered, rather than trying to say more ordered or more disordered. It's a little less confusing to say disordered every time. So let's think about some ways in which systems become more disordered, okay? So we said one already. If I go from a solid to a liquid, does that make the system more disordered? Yeah, so what do I call it going from a solid to a liquid? Melting, okay? So if I go from a solid to a liquid, what would the sign for delta S be? Positive or negative? Positive. Because we're increasing disorder, okay? So we use more kind of logic for these. Think about, does disorder increase or decrease? So from a solid to a liquid increases disorder. From a liquid to a gas also increases disorder. So what's the sign for delta S for that process going to be? Positive. Okay? So we're not going to write solid to gas. That's kind of understood here. If we have solid to liquid, liquid to gas, solid to gas is also a positive delta S. Who can think of another way in which entropy is increased? Tell me a specific example.
Like, when you don't close the system or something like that, you let particles escape.
We want to keep the sample the same.
Or like energy.
Let's come back to that. Yeah.
Something to do with pressure.
Let's come back to that.
It's positive.
Yeah, that's the easy way. We increase temperature. Okay.
Oh.
You said it gets more energy. I don't think that's quite the same thing. So we increase temperature, right?
Isn't that what changing from a solid to a liquid is?
Do we have a temperature change for a phase change or at a phase change? No. Okay. So going from a solid to a liquid is not a temperature change, it's a phase change. Okay. But can I increase the temperature of a solid or increase the temperature of a liquid or increase the temperature of a gas without changing the state of matter? Yes. Does that increase the energy and the motion of the particles? Yes. Does that cause them to be more disordered as their motion increases? Yes. So of these three changes so far, they're all positive changes. They all increase entropy. What would be the most positive change of these 1, 2, or 3, do you think? Probably 2, okay? Because there's a big change in the way those particles behave from a liquid to a gas. If you go from a cold liquid to a warm liquid, they change, but not a whole lot. The most drastic change is from a liquid to a gas or a solid to a gas, okay? What else? What if I had this example? If I wrote out H2O gas becomes H2 gas plus O2 gas. So when you see that reaction, your first urge should be to do what? Balance it. 2 there, 2 there. So I can talk about this in terms of 2 molecules of water or 2 moles of water, right? Either way, okay. So if, we'll just say molecules. If 2 molecules of water decompose to make 2 hydrogens plus 1 oxygen, 2 molecules became 3 molecules. Is that correct? So which of those sides would have the most disorder or most randomness? The reactants or the product side? The product side. Because 2 gases become 3 gases, okay? So we can say increasing the number of moles. And most importantly, I care about the increase in number of moles of what state of matter? Gas, okay? So you can also write beside it of a gas if you want to. Any ideas about the last one?
Wait, so the side where they're split apart, that one is more positive?
Yeah, but for that reaction, the overall change is positive. The last one's a little less kind of intuitive. It's going to be to dissolve a solid. So if you take solid sodium chloride, you put it in water, it goes from a nice crystal structure to a solution, so the solution is more disordered than the nice crystal structure is. So it tops out up here. If we want to find delta S, just like with delta H, we can find delta S of the products minus delta S of reactants. We really won't use that much, okay, just know that it exists. Entropy, just like with enthalpy, you can Google, and there are tables and tables and tables of values, okay. Just for enthalpy, I printed your notes, because we need those numbers. Because that's a useful measurement to us. Knowing how much energy is released is useful. Knowing what the disorder is, it's kind of a hard thing to think about quantifying anyway. We don't care so much about that for now. Just be aware those numbers do exist. But what's more important to know, positive delta S is increase in disorder, negative delta S is a decrease in disorder. Okay. So what you'll be asked to do is just predict the sign. Okay, so I'll give you a reaction or a process and say is delta S positive or negative for that. Can you all handle telling me that? Yeah. So if it's the reverse of one of these 5 steps, the sign for delta S would be what? Negative. Okay. So we'll focus for now more on predicting the sign. Okay. So kind of what this scale is set to, everything has some disorder. It was even the solid crystals have disorder due to their vibrations. So in order to have 0 entropy, we would have to have what kind of motion? Yeah, 0 motion, no motion, okay? So we kind of set the scale off of a crystal that's perfectly arranged. At what temperature is there no motion? So 0 Kelvin, okay? So the scale is kind of defined with 0 being the entropy of a crystal at absolute 0, okay? But delta S can go below 0, because that's not the value, that's the change in, okay? Kind of like delta H is the change in enthalpy, delta S is the change in disorder, where it's going to be positive or negative. Yeah. Yeah. So we now have this new term to talk about some factor that affects the reaction. We have entropy. So we see here that the temperature of a system affects its entropy, its disorder. As you increase the temperature, you also increase the disorder. So it's very common to see T delta S paired together. Okay, so we'll see temperature times the change in entropy. We'll talk about why in just a second. But as far as T goes, we're only worried so much about the sign of delta S. So we don't want the sign of T interfering with the sign of delta S. So what temperature scale should I use if I don't want the signs interfering? Kelvin. Do I have negative Kelvin I need to worry about? No. Do I have 0 to worry about? No. So if I plug in or use temperature in Kelvin, then the signs won't be flipped. We'll be good there, okay? So we say all that to say this. The new descriptor that we're going to use to describe equations is going to be kind of a term that encompasses all of the things we talked about. Okay, so the enthalpy, the entropy, the temperature. So it's kind of a measure of the total, we say free energy, so the total energy available in the reaction or in the system. So for that, we call it Gibbs free energy. So Gibbs is not a special thing, it was a man's name. It's just named after him. But for once, the symbol makes sense. So we want to talk about the change in Gibbs free energy. So what does the symbol start with if it's changing? Delta. So the symbol for change in Gibbs free energy is delta what? Why do you almost say Q? G, yeah. I heard Q. Delta G. So it finally makes sense, right? We have Gibbs free energy is delta G. So how we calculate delta G is delta G equals delta H minus T times delta S. So I got that again a little better. So delta G equals delta H minus T times delta S. That's the formula you'll have to know. So they might be thinking, why do I care about this? What is that? So we really don't care about the number that much for now. We'll do a little later. But for now we care about the sign of delta G. And there's some rules for that. So we come down here. So a positive delta G means a spontaneous reaction. Okay. So let's write it in and then we'll talk about it. I'll abbreviate. So sorry, I said it backwards. I was trying to talk around at the same time. Positive delta G is a non-spontaneous reaction. I'm sorry. Positive delta G is a non-spontaneous reaction. So what does non-spontaneous mean? Just in your own words.
It's nothing out of the ordinary.
It doesn't really happen on its own, okay? So if you're spontaneous, you do stuff on your own, right, without needing something influencing you. So a spontaneous reaction kind of happens on its own. Non-spontaneous does not, okay? So it's kind of a word we use in place of does happen or does not react, okay? So the negative delta G means what? Spontaneous. It kind of gives the definition of spontaneous. It happens without any assistance, okay? So it doesn't need an extra influence. So just because it's non-spontaneous, we calculate that, doesn't mean that it never could happen. Wait, say that again. Just because it's non-spontaneous, does that mean that it has no chance of ever happening? No. It means under the current conditions, it cannot happen. Okay? So if I say no reaction, that kind of implies this is never going to happen, never going to work, right? If I say non-spontaneous, that kind of means the way we currently have it, it won't happen, but it could later. Okay? So think about an example of that. So think about the lead in your pencil, we call it. What is the lead in your pencil made of? Graphite, which is just what element? It's just carbon. Okay, so graphite is just carbon. So what are diamonds also just made of? Carbon. Okay, so chemically they're made of the same atom. Okay, and graphite can be transformed into into diamonds. But if you just leave your graphite rod laying on the table, is it going to transform into a diamond? No. So is that reaction spontaneous? No, so it's non-spontaneous. Does that mean the reaction could never happen? No. It means under our current conditions, it cannot happen. But if we apply enough pressure and temperature, then it could happen. Okay? But under our current conditions we're dealing with, that reaction cannot happen. So that also means that if the reaction going from graphite to diamonds has a positive delta G, the reverse reaction, same with delta H, If the forward reaction is positive delta H, the backwards reaction has what sign of delta H? Negative. So the same thing applies here. So that would mean that the reaction from diamonds to graphite would be by definition spontaneous. So do you see your diamonds just turning into graphite all the time? No. So just because it's spontaneous doesn't mean it's going to happen or happen quickly. Okay? So kinetics is something we'll talk about in a couple of weeks. Kinetics is a measure of the rates of reactions, how quickly they happen. Okay? This is just a measure of, are they energetically favored? Okay? Can they happen? So just because we predict something will happen, does that mean that we're going to see it happen very quickly? No. So you can think about nuclear reactions. They might be favored, so they could be spontaneous, but they might take thousands or millions of years to happen. Okay? So the common mistake is here, when we get to the next chapter, and talk about rates and speed and kinetics, to associate spontaneity with speed. Okay? Whether or not it happens has nothing to do with the rate at which it happens. Okay? Questions about that so far? So really, what I care about from this formula, the number isn't so useful to me right now, but the sign on the number is. If it's negative, it's spontaneous, positive, non-spontaneous. Okay? So delta G, we measured in joules. Delta H is typically has a unit of joules or joules per mole. So delta G could be joules per mole or kilojoules per mole. So T, we said that's what units here? What are the units for temperature? Kelvin. Then delta S is going to be in kilojoule or joule per Kelvin. So the Kelvin cancels out there. Okay? So if I don't care so much about the number for delta G, I just care about the sign, do I have to actually plug in the numbers and calculate every single time, or can I just predict the signs? Predict the sign sometimes, okay? Because a lot of times we won't know the value of delta S, but I'll know the sign for it, okay? So let's think about, for example, if I have a negative delta H, what word describes a reaction with a negative delta H? Exothermic. And then I have a positive delta S. Let's think about it. If delta H is negative and delta S is positive, the value of delta G has to have what sign? It's got to be negative. Okay. Does the size of the number, does it matter? No. It has to be that sign. But there are situations, let's think about if delta H were positive and delta S were positive, can I automatically know the sign for delta G? No. A positive minus a positive can be positive or negative, right? 3 minus 2 or 2 minus 3. We can't know that all the time. So let's make a little kind of a chart to help us know when it's going to be negative or positive. So if we draw a little box, let's divide it up kind of into 4 little boxes. And we'll label it A, B, C, and D. So if I'm looking for the sign of delta G, I don't care about the sign on temperature, right? It's always positive. I have 4 different sign combinations for delta H and delta S. Plus, 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 minus, minus, plus, minus, minus. Okay? So if I put negative delta H here, positive delta H here, and I put positive delta S here, negative delta S there. Okay, so now let's write out the formula. Delta G equals delta H minus T delta S. Okay, so let's go through these combinations one at a time. So for box A, what is the sign for delta H? Negative. So a negative minus, what's the sign for delta S times T? It's going to be positive. So what is a negative minus a positive going to be? It's going to be a negative. So what do I describe a reaction with a negative delta G as? spontaneous. So do the numbers even matter here? No, there's no numbers I can plug in with a negative delta H, a positive delta S, and a Kelvin temperature where I get a positive delta G. So that must be a pretty good combination, right? If it's always spontaneous, let's think about what happens there. So negative delta H tells me endo or exo. Exothermic. So are the chemicals gaining energy or losing energy? They're losing. So they're going from high energy to low energy. I can put reactants, products. What's more stable? High energy or low energy? Low energy. Okay? So are the molecules becoming more stable as they move from reactants to products? Yeah. Is that a good thing? Yeah, they favor that. Okay? So then, that's why the negative delta H is good. And the positive delta S, disorder is doing what? Increasing. So we said that in the universe, an increase in entropy is favored. Okay, so we have two good things there, two positive not two numerically positive, two good combinations there. So when we have that combination, we always see a spontaneous reaction, negative delta G. So let's look at box D next. So box D, I have a positive delta H minus a negative delta S. A positive minus a negative is always what? It's always going to be positive. Can that ever be negative? No. So delta G is always positive with that combination. So what can I say about this combination? It always produces what? Non-spontaneous. So an endothermic reaction with a decrease in entropy is going to be non-spontaneous. So those are the two easy ones. Okay, those are the two combinations: a negative minus a positive and a positive minus a negative, where we always know the outcome. Okay, the other two are a little more complicated. Let's look at B. I have a positive delta H minus a positive delta S. So can I automatically know the sign of a positive minus a positive? Depends on the numbers, right? So let's think about, let's say delta S is bigger. Let's say this piece right here, the T times delta S, is bigger than this piece. If this piece is bigger, what's the sign for delta G going to be? Negative. Okay? So how do I make this piece bigger? What can I change about this to make it bigger? Temperature. So at a high temperature, are we spontaneous or non-spontaneous? Yeah, spontaneous. Delta G is negative. So delta G, what that was? Delta H and delta S are factors about the chemicals and the formula itself. They can't be changed. But T can be changed. For a reaction, I can change the temperature. That's the factor I can control. So then, if the size of this piece, the T delta S, is decreased, so a big positive minus a small positive, what is the sign for delta G? Positive. So spontaneous or non-spontaneous? Non-spontaneous. So if I have a reaction that falls into this quadrant right here, endothermic with a positive delta S, and is currently not spontaneous, what can I do to it to change that? Raise the temperature. Okay. We kind of have this preconceived notion that if you want a chemical reaction to work, if it's not, increase the temperature, right? And it'll make it happen. That's not always true. We'll look at that right here. So for this combination, negative minus a negative, we see the opposite. At a low temperature, we are spontaneous. And at a high temperature, we are non-spontaneous. And think about plugging numbers in there, and it should make sense. Okay, for C, a negative minus a negative. So for this situation, in quadrant C here, a negative and a negative, if we're currently non-spontaneous, will increasing the temperature help our situation any? No. Okay. So if we're in A and D, do we need numbers to predict spontaneity? No. If we're in B and C, do we? Yeah. But if I give you the values for B and C in these two boxes, could you plug in delta H, T, delta S, and get a value for delta G, and then tell me spontaneous or not? Good. Any questions about this? So let's kind of summarize what we've learned. So a lot of symbols, all right? We got delta H, delta S, delta G. And there's a positive and negative option for all those. Right? So let's talk about what those mean, just in one or two words. So in one word, a positive delta H means what? Endothermic. Positive delta H is an endothermic reaction. What is a negative delta H? Exothermic. Okay. So in a few more words, negative delta H, energy released, positive delta H, energy absorbed. Okay. Then for delta S, in two words, what does a positive delta S mean? Not for delta S. What does S stand for? Entropy. So what does a positive delta S tell me? Yes, increase in disorder or more disorder. Okay. So what does a negative delta S tell me? So you can say more ordered. Let's say less disordered, though, to make it a little easier to remember. So more disordered or less disordered. Okay. Then for delta G, when we really care about now, a positive delta G tells me what? Positive delta G is non-spontaneous. Negative delta G is what? Spontaneous. Okay, so a lot of symbols and plus or minuses to remember there. Okay. Any questions about any of that? Good. So that's all the new material for this chapter. We'll stop right here and I'll give you your last test back. So not too bad.